Hi everyone, my topic is linear programming. So in our life, we usually have all kinds of problems that requires us to do the optimization. So here is an example that a chocolate company wants to maximize their profit. So talking about linear programming, that example is previous problem is an example of linear programming. So linear programming is a class of optimization problem that consists of linear constraints and objective function. It was firstly introduced by Leonard Kantorowicz in 1939, and later in 1946, Danzig invented the simplex method for the first time, and it solves the linear LP problems time efficiently. And later in 1979, Leonard Kanchian invented the interior point method, which is called the ellipsoid method as well. It is solving the LP problem in polynomial time, which is more efficient than the simplex method. But in our presentation, we'll only talk about the simplex method. So consider an LP problem that has three constraints and objective function that we want to maximize. We need to our first step of simplex method is to adding the slack variable to all the less than constraints and adding surplus variable, which is a negative variable, to all the bigger than constraints to make the left hand side equals to right hand side. So our LP problem will be transformed into a matrix which is called tableau in the simplex method, like this. So notice we have an extra column on the on the leftmost side. It is called the active variable. We'll find so how do we find an active variable? So for each row we'll need to look at the value or to check if all the values above or below this value is 0, and this value should be 1. If we find such a location, that it is a pivot, and the variable in this column will be assigned to this row. So in this case, the first row will have the pivot here, and they will then assign S to this row, and and then we will find our solution by using the values in the answer column divided by our pivot value of our pivot. And so 40 divided by 1 is 40. So we will find that S equals 40, T equals to -10, and U equals to -10, and all other variable equals to 0 if it is not an active variable. And notice we will star a row if the active variable is negative, and we will and our goal is to find a feasible and optimal solution. Notice a feasible solution is all the variables larger than 0, and an optimal solution is there are no negative coefficient in the last row. So our current state is not feasible and not optimal. So we will transform our tableau. So third step of the simplex method is to find a pivot. So we will need to find the pivot column first. So we will have two cases. The first case is we have star row. If we have star row, the pivot column will be the largest positive number in the first star row. If we don't have star row, if we have done fixing all the star row, the pivot column will be the smallest negative number. Will be the column that having the smallest negative number in the bottom row. And once we find a pivot column, we will need to find the row one row from we'll find a pivot row. We'll need to do the test ratio again, like what we did in the previous step. We do our test ratio by using the values in the answer column divided by the value in the pivot column. So we'll need to. So our pivot row will be the smallest non-negative test ratio. After find a pivot, we'll need to do the pivot operation, which is by using a row operation, we'll make all the coefficient above and below our pivot equals to 0, and we also need to make our pivot equals to 1. So this tableau after we do the pivot operation will become like this, noticing all the values above and below 1 is 0 now. And we need to repeat steps 3 to step 4 many times until we have an optimal and feasible solution. So we'll get our final tableau here like this after we repeat our step 3 times. So our solution will be the active variable equals to the values in the answer column. So y equals to 10, the x equals to 10, that equals to 20, and p, which is our objective function, equals to 70. So after introducing the simplex method, we will talk about an application of the linear programming, which is linear regression. It is a classic set of problems that we need to model the linear relationship between a dependent variable y and an independent variable x, xi to xn. So given a data point that has an independent variable, our goal is to find a set of variable beta 0 to beta n that such that we make our left-hand side of our equation equals to right-hand side as close as possible. Usually we use the least square approach, but in our case we're gonna use the absolute value of our difference, and we define z that is equals to the max of the absolute difference, and our goal is to minimize that. So given a data point that has y and independent variable, we'll find our constraint like this, which is the beta times x minus our dependent variable is as less than that, and we can convert our constraint into a more LP problem-like constraint by moving our constant to the right and our variable, which is that to the left. And our goal is to solve for beta 0 to beta n that minimize our depth. So after inserting select variable and surplus variable, an example of 2 data point 1, 3, 2, 8 will generate a table like this. Next thing, we just want to use our simplex method to solve a tableau, and we will find our final decision to make our value, to make our objective function to the small. Thank you. That is my presentation. Thank you.